Data from model, extracting data from non-robust and robust models. Despite their great success, deep neural networks are also known to be vulnerable to adversarial examples. These are small perturbations in the image which can lead to misclassifications. Such changes are mostly imperceptible for human observers. In the machine learning community, this perturbation is in general treated as special noise that perturbs the images. One famous technique, deep fool, is inspired by this perspective and utilizes malicious noise to fool an image across the decision boundary. Recently, Imtiaz et al. Provided a new perspective on adversarial examples. Specifically, the authors attributed the success of adversarial examples to the existence of non-robust features in a dataset. They obtained a non-robust dataset from a standard model by generating adversarial examples for the original training dataset. This dataset still looks like the original training dataset for a human observer, but contains non-robust features for classes different from the real ground truths. A model trained on this dataset generalizes well to the original validation dataset, but exhibits low accuracy when evaluated under adversarial examples. The authors repeat this process on an adversarially trained model. The obtained dataset was assumed to mainly contain robust features. A model trained on this robust dataset shows good generalization performance to the original validation dataset and further shows a relatively high resistance to adversarial attacks. Their results suggest that features can be seen as the link between data and model. Data is widely used in deep learning to train a model, which we term data to model, or in short DtM. For a better understanding of the relationship between data and model, we explore its reverse process of data from model, or in short DfM. DfM can be interpreted as a feature extraction process from the model to the data. We benchmark the work by Imtiaz et al. And apply the following modifications and extensions. First, their work only explored DfM and DtM in one single iteration. In this work, we iterate this process in chains. During the DtM and DfM process, we assume access to only either the data or the model generated in the previous process. Since the access to the previously trained dataset is not granted, we leverage a substitute dataset as background images as well as virtual logits. We choose FashionMNIST and MS-COCO as background images instead of MNIST and Cypher10 respectively. The virtual logits are randomly sampled from a heuristically chosen Gaussian distribution. For the DtM process, we found that training the model with the MSE loss contributes to better performance. With the MSE loss, the generated model can even outperform the original robust model on the original validation dataset. The process of sequencing DtM and DfM is indicated in Figure 1. Table 1 shows the evaluation of the models at different stages during the chaining process on the original validation dataset. In the first few stages, comparable performance to the original model can be observed. Nonetheless, a general trend of accuracy degradation for both the non-robust and robust models for each sequence is observed. Table 2 investigates the robustness to adversarial examples for the obtained LeNet models. Similar to the observed accuracy during the sequenced process, a trend of decreasing robustness is observed during the sequential process. With increasing steps, a shift from robust features to more non-robust features can be observed. The robust accuracy decreases significantly faster than the standard accuracy. After two subsequent DfM iterations, starting from the robust origin model, the resulting models still show similar robustness as the standard non-robust model. The qualitative results show that the extracted images look totally different from the original images for a human observer. However, the achieved comparable performance indicates that similar feature mappings between the datasets exist. In our cross-training experiment, we applied DfM to a model and trained different state-of-the-art architectures on the extracted data as indicated in Figure 1. The results in Table 1 show that all model architectures can be successfully trained on the extracted data with negligible performance variation. It suggests that the features in the regenerated dataset are not inherent to any specific architecture. For the robust models, one interesting phenomenon can be observed. The retrained models consistently outperform the corresponding robust origin model for both similar and different architectures. The goal of our cross-evaluation experiment is to analyze whether different models trained from the same origin dataset learn the same or different feature mappings. Table 1 reveals that cross-evaluation accuracies are higher than random guess, which indicates that some shared feature mappings are learned. However, only in a few cases an accuracy higher than 50% is achieved. The relatively low cross-evaluation accuracies illustrate that models learn different features which are not fully compatible with each other. In this work, we introduced the data from model process by extracting data back from the model using a substitute dataset and virtual logits. We showed that the DtM and DfM process can be performed in sequence and that the performance and robustness of the models can be partially sustained during this process. Further, we provided evidence that model architectures are not limited to only be trained on the data extracted by themselves, but can also be trained on the feature mappings of other architectures.